Hey everybody, so limiting reactants and percent yields wraps up chapter 3 for us. We're going to dive back into chapter 4 now to finish the second half of our second unit of the year. Chapter 4 in the text is called Aqueous Solutions and Types of Reactions. And today our job is going to be to kind of define what a solution is and take a look inside of a solution. We want to see what's actually happening in there. First of all, a solution is going to be defined as a homogeneous mixture. And as we probably understand, solutions are typically liquids. Okay, not always, but they can typically be liquids, all liquids. There's really two parts of a solution. The first part being the solute. That's the thing that's getting dissolved. The second part being the solvent. That's what does the dissolving. So in most cases that we're aware of, the solvent is water. And then the solute is some other type of solid, usually. Salt. We can dissolve salt into water. In that case, the salt, table salt, NaCl, would be the solute. If something is soluble, that means it can be dissolved. So if I were to ask you, is table salt soluble, you'd say yes. If I were to ask you, is vegetable oil soluble in water, you would say no. It's important, though, to make the distinguishment of what the actual solvent is. There are certain things that vegetable oil is soluble in. Water just doesn't happen to be one of them. And then the last thing let's talk about is miscible. If something is miscible, if two things are miscible, that means that there are two liquids that can dissolve together. Ethanol and water are miscible. Vinegar and water are miscible. Soda and water are miscible. Vegetable oil and water are not miscible. Okay, so that's the terms that we should probably have a pretty good handle on. Now, what's happening inside of an aqueous solution? An aqueous solution means that there's something dissolved in water. So the term aqueous, as we've defined it, typically with AQ in parentheses, means that whatever we're talking about is dissolved in water. You can hear the term aqua in aqueous. And water is a good solvent because the molecules, water molecules, are polar, a term that we've talked about in the past. And by this, again, I mean that the oxygen atoms have a partial negative charge. If the oxygen atoms have a partial negative charge, the hydrogen atoms have a partial positive charge. So if we draw that on a diagram here, we'll notice that the electrons are more towards the yellow atom on the right side of our page. So we have a partial negative charge over here, actually a 2 partial negative charge. And we have a partial positive charge. Let me go back here. Partial positive there, and a partial positive there. Okay? So the hydrogen, which would be the blue ones, this is your hydrogen, and this is your hydrogen here. Their little electron that's flying around them is actually being pulled really close to the water molecule. And that's why the water molecule now has that partial negative charge. And because the hydrogens are essentially giving up the electron, they've lost the negative thing, so they become partially positive. All right, so one of the reasons why water is so good at being a dissolver is A, it's a polar molecule. Half of the molecule is positive, half of it's negative. And B, it's actually the shape of the molecule. The angle that I'm going to draw here is actually at 105 degrees. This angle right here is 105 degrees. And that's important because we can essentially see that we have two halves of our molecule. You can kind of like draw a line all the way down the molecule. And we have two halves. We have the negative side right here, and we have the positive side over on this side. And it's that idea that's going to allow water to be a great separator of ionic compounds. We know that ionic compounds are made of positive and negative charges. So if we have something like water that has a positive and a negative side, it's going to act like a magnet that sucks apart those ions. This process of breaking ions apart, breaking salts apart, is known as hydration. Ions have charges, so sodium chloride, the Na is positive and the Cl is negative. Ions have charges and attract the opposite charges on the water molecules. We call this, it's got two big terms, two common terms. This is either called dissociation or it's called ionization. Okay? Okay, so you're going to hear me use those terms almost interchangeably. So let's get a visual of how this works. Okay, here's my ionic compound. It's got a bunch of positive charges, yellow with the black crosses, and a bunch of negative charges, blue with the yellow negative signs. So here's my ionic compound, and let's bring water into play here. So water is added to the ionic compound, or the ionic compound is added to water, whichever you like. And as we said, the hydrogen is partial positive charge, the oxygen is partial negative charge. So where do you think the ions are going to go? Well, hopefully you understand that the negative ions will get pulled towards the hydrogens, the positive pulled towards the oxygens. And we actually now have this pulling apart of our traditional ionic crystal. This, again, is known as dissociation or ionization. And because we're adding water to the substance, we can also term it hydration. Now, I do understand, and I want you to understand, that this process is not a chemical process. This is a physical process, dissolving. Because if we really wanted to get the salt back, we certainly could. We could dissolve the water and the salt would then reform. It'd look a little bit different because the crystal would look different, but it would still be the salt. So this is a physical change. However, we can still write equations that describe this dissociation. Okay? Let's take a look at the first one. NaCl, that's very traditional. When you would take one formula unit of NaCl and you'd place it into water, you'd get a single sodium ion and a single chloride ion. So if you'd put 1 mole of sodium chloride into water, you'd get 1 mole of sodium ions and a mole of chloride ions. Okay? You can see the stoichiometry kind of works itself out. Here's a different case, though. Magnesium chloride. This is still a salt. Okay? It's still got an anion and a cation. And if I place this into water, if I place 1 mole of magnesium chloride into water, what do you think I would get for the amount of moles of my products? Well, hopefully you'd understand that, again, I'd get 1 mole of magnesium ions, but I'd get 2 moles of chloride ions. Okay? And the reason I have to do that is, or the reason that that occurs is because of the coefficient in front of the chloride ion. So when we were doing solutions, and when we were doing molarities of solutions, we did run into a couple of problems like this. And they asked, if we do dissolve an ionic salt compound into water, they asked us what would the molarity of the ions be. Well, now I hope we have enough knowledge to be able to figure that out. It comes from these dissociation equations, the mole ratio. I have the question at the bottom, how many moles of chloride ions are produced when 1 mole of magnesium chloride is dissolved in water. Let me just quickly go through the stoichiometry that would entail. It's pretty simple. So you've got 1.00 moles of the MgCl2. And you're just going to do a mole-to-mole ratio. For every 1 mole of MgCl2 placed into water, you're going to produce 2 moles of the chloride ion. There it is. And that comes from the coefficients. So your answer here would be 2.00 moles. Now this is very easy. It's a one-step problem. But it is a component that will help us complete larger problems, 6, 7, 8-step problems later on down the road. All right, let's get back. Now, I want to talk about a term called solubility. Not all substances are created equal. All right? Solubility refers to how much of a substance will actually dissolve in a particular amount of water. How much of a substance will dissolve in a given amount of water. This is usually given in terms of grams of substance per 100 milliliters of solution. It varies greatly. Okay? There's a huge wide variety of how solutions will dissolve. Salt does a really good job of dissolving in water. Other things not so well. Silver chloride, for instance, doesn't dissolve as well. So this varies greatly. But if the ionic substances do dissolve at all, then the ions are separated, and they can always move around. Okay. Now, when we get to this solubility idea, I'm going to go back here once. When we get to this idea of solubility and how soluble an ionic compound is, that's actually something that we're going to save for a little bit later in the unit when we talk about solubility rules. So there's actually, we can calculate how soluble each one of the compounds is, and we're going to save that to a little bit later on in the course. Now, water can also dissolve non-ionic compounds. Up until this point, we've been talking about water being a great dissolver of ionic compounds, sodium chloride and magnesium chloride. But it can also dissolve non-ionic compounds if they have polar bonds. A great example is water's ability to go ahead and dissolve ethanol. Ethanol is the alcohol that is infamously, I suppose, contained in alcoholic drinks. And alcoholic drinks are primarily water. So in order for this type of drink to be produced, the ethanol has got to be dissolved inside of the water. Otherwise, there would be this separation inside of the drink, and it wouldn't be as appealing to those that actually drink it. So here's my water molecule, or my ethanol molecule that I've got on the bottom of the screen here. And you can see this end right here actually looks an awful lot like water. There's an O and an H, and there's a bend to those molecules. Because of that bend, this oxygen has a negative charge, this hydrogen has a positive charge. And so when water comes into play again, having a negative side and a positive side, it's able to attach itself to the ethanol molecule and thus dissolve the ethanol molecule. So it doesn't have to be an ionic compound for it to actually dissolve. All right, let's go a little bit further in classifying solutions and their ability to dissolve. A term that we use to classify these types of solutes is an electrolyte. Solutions of ionic compounds can conduct electricity. You probably heard the term electrolyte before with a Gatorade or a Powerade or some type of energy drink. These types of electrolytes, there's three different types. We have three different types of electrolytes. We have strong, we have weak, and we have non-electrolytes. And the diagram that I have here on the bottom hopefully shows the difference between those two. If you look on the right side of the diagram, you see a whole bunch of ions in solution, and those ions are totally dissociated, so totally broken apart. And you have the positive ions going to this side, the negative ions going to this side, the positive node, and as you look at the light bulb down here, it's glowing, it's turning on. The ions are allowing electricity to flow. Okay? They're helping the flow of electricity. And because of that, our little light bulb here is actually going to glow. And I'll show a demonstration of this in class tomorrow. Now in the middle, a weak electrolyte, only some of the ions are dissociating, not all of them. And in this case, again, the positives are going to the negative side, and the negatives are going to the positive side. And as you look at the light bulb, hopefully you can tell there's a difference in the brightness of the bulb. There's not as much electricity flowing. And this defines a weak electrolyte. Finally, we have a non-electrolyte. Sugar would be a good example. If you put sugar in water, sugar doesn't dissociate at all. So you've got nothing going to the negative electrode, nothing going to the positive electrode. So electricity can't flow, and there you see a light bulb that's not illuminated. So let's talk about strong electrolytes first. These completely dissociate. And that means that they completely fall apart into ions. So there's many ions, and they're great conductors. Weak electrolytes, on the other hand, only partially fall apart into ions. So there's few ions, and they only conduct electricity slightly. And finally, non-electrolytes. They don't fall apart at all, they have no ions, and they don't conduct. Again, sugar would be a good example there. And we can get some specific types of these electrolytes. Acids. Acids are usually great examples of electrolytes. If you have a strong acid, that means it's a really, really good electrolyte. That means that it falls apart completely, unless it has many ions. So I've got some examples here, some strong electrolytes. And let's take HCl for a second, so that's stomach acid. So you have hydrochloric acid. Any acids always get the aqueous designation there on the bottom. Okay. And that dissociates into the hydrogen ion and the chloride ions. It's an AQ, and that's an AQ. And it does it 100%. So if you have 100 moles of HCl, at the end of the day you'll have 100 moles of hydrogen ion and 100 moles of chloride ion. And that's what makes HCl so incredibly strong. The rest of those acids, sulfuric, nitric, hydrobromic, hydroiodic, and chloric acid are also very strong. Weak acids don't dissociate completely. Acetic acid is a good example of this. So instead of dissociating 100%, actually acetic acid only dissociates about 1%. And when we write, let me go back here, when we write the equation for that dissociation, instead of writing a single arrow, we actually write a double arrow. It's called an equilibrium arrow. So some of the ions do produce, but some of them stay in the C2H3O2 form. Okay? And actually only 1% ionization for acetic acid. So the light bulbs surely would not glow as bright as it would with the hydrochloric acid. There are opposites of acids. We call these things bases. We'll talk about the pH scale later on in the chapter. Bases form hydroxide ions when dissolved. There are strong bases that produce many, many ions, and two of the most common examples are KOH, potassium hydroxide, and NaOH, sodium hydroxide. All right, and that's all we got. It's a long one. Thanks for paying attention.